I don't know
Go!
what's been going
Okay, good. Thank you for the reminder. Got it. Okay, so now let us talk about antennas because this is actually perfect timing because this is where we were headed into yesterday. So, this is a fundamental antenna. This is the most basic antenna. This antenna is a half wave long. It has two legs. This is, if you want to say, a pole, and this is a pole. This would be pole number one, and this is pole number two. It has two legs. This is called a dipole antenna. In particular, this dipole antenna is a half wavelength long at whatever frequency we happen to be measuring. So this antenna is called a half wave dipole. And does everybody remember this little letter lambda? Right? That's
Right.
short for a wavelength. This is usually measured in meters. Right? So this is our wavelength. And it's measured in meters. So a half wave dipole is kind of the fundamental antenna that exists in nature. So now the question really is, why is this such an important antenna? The reason being, I'm going to ask a question. So we're going to get to current very shortly. Current is the flow of electrons. All right. So let's take a look at an atom. We have our nucleus, which is protons and neutrons. Protons are positive, neutrons are zero charge and flying around in orbits, small and big. We have electrons. Electrons are tiny particles that have a negative charge. A neutral atom has a net zero charge. If we push an electron into an electron is typically going to pop out unless there's some compelling reason for it to stay. Metal is really good at doing this. So, if this is copper, for instance, if you push an electron in, you get an electron out. That movement of an electron through something is known as current, which we will get to very shortly when we start doing electronics. Okay, so now, here's a question for you. If I look at the end of a piece of wire, just a piece of wire that's made of copper, which is a good conductor. Conductor means that electrons can move through it very easily. How many electrons are coming from outside into that wire from empty space?
I would say zero.
Practically zero. That's right. So the important thing to note here is that if this is a piece of wire, the current, which is the amount, the net number of electrons flowing at a given point through something, is zero. So what does it have to be at the other end?
Zero.
It has to be zero. So this is an important thing to remember. Typically, the current, unless there's a corona, unless there's like lightning coming off of it, unless that exists, the current at the end of a piece of wire is zero. Okay? So now, I'm going to just start drawing a wave. Does everyone agree that this is a wave? And in particular, a sine wave. Everyone agree with that?
Yeah.
Okay.
Yes.
So let us take this antenna, this piece of wire. We're going to draw a new one so that it fits onto this so that it meets those requirements. So what did we just say at the end of a wire that our current has to be? It has to be zero,
Zero.
right? According to this map, I see 1, 2, 3 times that it's zero. Everyone agree with that?
Yep.
Okay, so I could do this and take this section and put a wire on this right here, and that wire would actually meet the requirement, right? If I were to take this piece of wire right here and turn that into an antenna, I could get a zero there and a zero there. Now, I could also do something, and I could do this. I could take a piece of wire and pick an end right there, and I could also pick an end there. And that would also be, that would also meet the requirement, would it not? Right?
Yeah, should.
I could also do another one, let's say, where I started here and went 1, 2, 3. And pick an antenna that had those ends. That would also be something that met the requirement. So now, what's important to note here is we're dealing with a couple of different things. This is the smallest antenna right here, for which that happens to be true. And it happens to be 1/2 wave, which is why a half wavelength dipole antenna is the simplest antenna. It's kind of the fundamental building block. So if that's a half wave antenna, how about this one up here? What would you call that?
Full wave.
You'd call that a full wave or a 1 wave antenna, a 1 wave dipole. How about the yellow one?
1.5 wave.
Yep, or a 3/2 wave dipole. Exactly. Okay, but now at a given frequency, what we didn't draw the same way is the fact that a wavelength is a wavelength is a wavelength. At a given frequency, that wavelength is fixed. So which is going to be the shortest of all three? Remembering I didn't draw them to scale.
A half.
A half. So there you go again. Okay, so a half is the simplest and smallest antenna that meets those requirements. Okay, now, interestingly, if this is a map of our current, which is the flow of electrons, where is the current at its highest? That would be right in the middle. So, as it turns out, I'm going to write Ohm's law right now, which we're going to do in just a little while in the electronics portion. E is equal to I times R, where E is your voltage, and I is your current, and R is your resistance. So what it turns out here is that we can rearrange E equals I times R, and we can make it R is equal to E divided by I, which is our voltage, which is E, divided by our current. Well, if we know that our current is big, our voltage, if we were to draw it, would actually probably look something like this, and would have a minimum point right at the center. So if our current is very big and our voltage is very low, qualitatively we have our resistance is low divided by high. If something doesn't resist us putting energy into it, that means that it's easy to put energy into. Well, that's a pretty good antenna for that. But now let's take a look at this green one up above. Right? So we have our high voltage at the same point where our current is low. We're going to draw this wave like that. So what happens at the center point? We have how much current? We have 0 current, or very low current. We also have very high voltage. Qualitatively, what happens there is that our resistance is equal to E divided by I, which is equal to high divided by 0. What's something divided by 0?
Always.
Well, essentially something very
Infinite.
big or infinity. Try pushing power into something that has infinite resistance, and what happens? It becomes very hard to do. So you can do something like this, but it becomes extremely difficult. Now, it turns out that a 3/2 wave antenna is really just a center-fed half-wave antenna with this and this hanging off the ends. So that actually kind of works. The other thing you can do is you can actually take the feed point and move it over here, in which case this now becomes a half-wave antenna with an extra little thing hanging off of one side, which will make it unbalanced. And that's why a half-wave antenna is the simplest, and notice it's symmetric, easiest antenna to make, easiest antenna to model, easiest antenna to build. Okay, so now that we have this thing called a half-wave antenna, we're actually going to say, how long should it be? Now, does everyone remember this formula that we did yesterday? Everybody remember we did that?
Yes.
To basically link together our frequency and our wavelength? Okay, so what we're going to do is we're going to make an antenna for the 40-meter band, and we're going to pick a frequency of 7.250 megahertz. Okay, so the first thing we have to do is now we're going to say, what is our wavelength? 40 meters is approximate. Our frequency is exact. So we're going to say we don't know the exact wavelength. So now we have this right here. Wavelength is equal to 300 divided by 7.250. And because I can't do that correctly in my head without making some mistakes, 300 divided by 7.25.
4137.
41.3, I'm going to round up, 41.38 meters. Okay, so that is a full wavelength. How long did we say we want that antenna to be? How many waves?
Half.
Half wave. Okay, so a half wave is now half of that. And I get 20.69 meters. Okay, so that would be a full half wave. Well, this is where the math and reality diverge a little bit. What ends up happening is that we have to take roughly 95% of this. And that is because the real world is not perfect. We basically end up with a little bit of...
Yo.
Yes. We basically end up having to knock 5% off the length of the antenna because, again, it tends to couple with itself. It tends to couple with other things. We're going to get to that as well. But when I say couple, essentially the fact that there's a wire in space all by itself, in this case, it's not in space all by itself. There are trees around, there are buildings, there's all kinds of stuff. And that and wires are not infinitely narrow, nor are they infinitely conducting. So we end up knocking 5% off the length. So we're going to multiply this by 0.95. And that gives us 19.66 meters. And now we're going to take this and convert it to feet. And it's roughly 3.3 feet per meter because most of the world works in meters. And we get 64.86 feet long. So typically what you would do in this case is you'd say, okay, we're going to make this antenna 65 feet long. That's a half-wave dipole. That's the total length of the antenna. And that is how you make an antenna. If we were to make an antenna that was only a quarter wave, so let's say we had a quarter wave antenna over a ground, which is a conducting surface. This is a quarter wave antenna. It basically echoes the other half of the antenna, makes it look like it's actually a dipole, except it's not physically there. Then it would be half of that length. So this would then be about 32.5 feet. So now what we have is really important because what we've got is the fact that our antenna length is now directly coupled to our frequency. Is it not? If we know what frequency we're operating on, we know how big the antenna is supposed to be.
Scott, you just mentioned making a quarter wave antenna.
Yep.
Why would one do that?
Well, let's say that you're putting something on the roof of a car. Okay? In fact, let's do this. Somebody give me a frequency in VHF. Just pick one. It's good practice for what VHF is. So we saw what? We had somebody say 132 megahertz. Okay, that's right squarely in the AM aircraft band. But that's fine. It doesn't matter. Okay, so what we're going to do is we're going to do our calculation again. 300, F, and lambda, just like that. So we don't know our wavelength. F, or our wavelength, is equal to 300 divided by F is equal to 300 divided by 132. Grab the calculator again. 2.27 meters. Might as well convert it to feet. We get 7.5 feet. Okay. That is a full wave at 132 megahertz. So a half wave is 3.75 feet. So if we made a half-wave dipole, it would be 3.75 feet long. But let's say, why would we want to do that? Okay, so we're going to look at this thing called a dipole. And a dipole, it's very important to think about axes of symmetry. So if I have this piece of wire, I'm going to erase the feed line. If I think about this piece of wire, does it matter if the wire is turned vertically like this? Yes, it does, right? I mean, it'll be a totally different antenna. The polarization will be different. This is parallel to the ground, so that's a horizontally polarized antenna. And this is vertical to the ground. So that will be a vertically polarized antenna. They're totally different antennas. Now, does it matter if I take this horizontally polarized dipole and I take it like this pencil and I roll it? Can you see any difference at all if I rotate it like this?
No.
None. Which basically means it doesn't matter what it looks like, which means that it has an antenna it has a pattern that basically is the same in this direction and this direction, and if I could draw it coming out of the page toward me and going into the page away from me and in all directions around it. So if I were to look at it from the end, it would actually look kind of like a donut. The radiation pattern of a dipole kind of looks like a donut around the wire.
Wouldn't the magnetic field be oriented differently if you twist it?
Yes, but the electric field is what determines the polarization. And actually the magnetic field, it wouldn't make any difference because the electric field is the same. Basically, the magnetic field is kind of like around in a circle. So the radiation pattern of a dipole, if we look just at it from the side, it would look like we cut into a donut. And the donut would be like this, and the donut would be like this. And so a dipole would generate energy upward and downward and toward us and away from us. And it generates absolutely nothing along the axis of the wire. Okay, so can you think of any good things about this?
No.
I can.
Physical installation problem?
Yeah, well, I mean, good things. You can put this up on a tower and rotate it, right? And if you rotate it, what happens to the donut?
It rotates also.
It rotates, so you have a directional antenna. Now, what's the only problem with this antenna? Where's some of your energy going? Straight up into the sky. And some of your energy is going
the ground.
Straight down into the ground. That doesn't really do you a lot of good. Now, what if you could take this antenna instead and do this with it? And make it vertical. Then your donut would look like this. Agreed?
Yeah.
Yes.
I've just rotated my donut 90 degrees. Okay. Can you think of any big advantages to this?
All directions.
All directions. And how much of your signal goes up at the sky?
0.
Not much.
Not much. How much goes down into the ground?
Not much.
Not much. All right.
But then you're limited to a certain height.
You're limited to certain height. That's right. So let's say that this is an antenna that is only, like we just calculated, 3.75 feet long. Well, that's a piece of cake. You can put that on a rope and haul it up a tree, right? What if this antenna at a given frequency is 425 feet long? Not so easy.
That would have to be a real big.
You'd need a really big tree. Yeah. Or you'd need a freestanding tower or something. So,
Yeah.
so now let's take a look at what we just did. We said, okay, we calculated our wavelength of 3.75 feet. Or sorry, our half wave antenna. So that's the antenna we just came up with, 3.75 feet long. Okay, well, we could actually try to put up a half-wave vertical. Let's say we wanted something on the roof of our car. We could try to put up a half-wave vertical on the roof of the car, but it turns out that a half-wave vertical is actually difficult to feed power into when you're feeding it at the end. Because what's the current at the end of the antenna?
Low.
It would be 0, which
0.
means that the feed point resistance is very high. So this is actually a very difficult antenna to feed. Well, as it turns out, what we can do with this antenna is we can make half of it go away. And we can take this whole thing and we can move the roof of the car, for instance, so that the roof of the car is right here. And the roof of the car is coupled to the other half of the antenna. And because the roof of the car is made of steel, which is a conductive material, what it ends up looking like is that the other half of this antenna is actually mirrored in the roof of the car. So this is a quarter wave, which is physical, and this is a quarter wave, which is imaginary. Now, I can show you what this looks like and make you believe this little parlor trick.
Now, does it actually have to be bonded?
It does not have to be bonded. It can actually be capacitively coupled.
So, would it work if you just stuck the antenna on with a magnet?
Yep. And that's because the base of the magnet is capacitively coupled to the roof of the car.
Oh.
Again, a neat parlor trick. Okay, so here we go. Ready? All right, so I'm going to hopefully turn this off. And I'm going to turn this flashlight on. Okay, ready? Can everybody see this light?
Yes.
Okay, now I'm going to do a little trick here. If you didn't know that I was holding an iPad here, let me see if I can arrange it so that there's actually 2. There we go. How many lights do you see if you didn't know there was an iPad there?
2.
You'd see 2. That's right. In other words, by putting something that was a reflective surface in the right spot, you as the viewer have absolutely no idea what's there and what's not. And it doesn't even matter. As far as you're concerned, it does exist. And here is why that works. So let's say that you are over here and you're looking at this antenna, which we're just going to use as a dot. But what you see is this reflective surface. You're actually seeing a reflection of that dot. But yet, since you don't know there's a reflective surface there, you're actually seeing that. It looks like 2 antennas. That is what a quarter wave antenna over a ground plane looks like to the rest of the world. What is this antenna known as to the rest of the world? How long is it? If this is a quarter wave, how long is the whole thing?
Halfway.
That's a half wave. That would be a half wave dipole. So what you've basically just done is trick the world into thinking that you really have a vertical half-wave dipole set up on the roof of your car.
Does
That
the
the roof of your
placement
car doesn't even exist.
does the placement of the quarter wave antenna matter?
Yeah, I mean,
Or
the
the
closer
shape?
to the center it is, the better. But now, here's another question. Let's say that I was lucky enough to have a car that had a fiberglass roof. And I used crazy glue and put my quarter wave antenna on the roof. Does it work or not?
Good.
Hmm?
Wait, no, it wouldn't because
would not
it's
work.
not a conductive surface.
Because it's not a conductive surface.
Because
Exactly.
all fiberglass is just.
Yep. Fiberglass is an insulator. That would not work. So let us say that instead I were to take my quarter wave antenna and bring it inside and stick it on a wooden table. What do you think? Good or no?
No, because
Nope.
wood is a not a conductor.
Okay, here's the next one. Let's say I bring my quarter wave antenna, I bring it inside my house, and I stick it on a steel pie pan.
That should work because it's conductive.
I have done this. I've actually done this many times.
Anything metal, it should conduct.
Yep.
And anything that uses wiring.
Yeah.
That's
Exactly.
metal.
That's metal. So in particular, if it's like, for instance, a pie plate or a baking sheet, that actually works well. The top of a refrigerator, that actually works really well as a ground plane for an antenna.
Mini pennies, yes.
Yeah.
All pennies are a thin layer of copper and zinc.
Okay.
Sure.
So let's take a look at these questions. We're on antennas and feed lines. We're going to do feed lines a little bit later. Which of the following describes a simple dipole-oriented parallel to the Earth's surface? That would be a horizontally polarized antenna. In which direction does a half-wave dipole radiate the strongest signal? And the
Scott,
answer is,
what page are you?
I am on 33.
Okay, thank
And
you.
that's known as broadside to the antenna. It doesn't radiate any signal in the direction of the wire itself. It's broadside, so perpendicular to the wire. The approximate length of a half-wave 6-meter dipole antenna, we could figure that out by doing the math. The same thing with a quarter-wave antenna. We could figure that out by doing the math. We just proved that it works. So, if you find that your antenna is operating on a frequency that is too low, what would you do to raise the frequency of the antenna? Has anyone ever played a musical instrument like a flute or a clarinet?
Yeah. Shorten it.
You shorten it. That's right. Because what happens if your tuning is too low? That means your flute is too long. You have to tighten it up. If you're, for instance, it's a resonant pipe. An antenna is a resonant wire, just like a musical instrument, like a clarinet or an oboe or a flute, is a resonant tube.
Are there any advantage or disadvantages to rubber ducks?
We will get to that. That's coming.
Okay.
Okay. How many wavelengths long is a quarter wave antenna?
Quarter.
Quarter wave. Okay.
Quarter.
However, not exactly a quarter, because when you calculate an antenna's wavelength, what do you have to do?
Less
95%.
You have to shorten it by 5%. That's exactly right.
Scott, I have a question.
Yep.
So you mentioned musical instrument. There's a significance to whether or not both sides are open or closed.
Correct.
Is there?
There's no what's the word for it? There's
Anything comparable?
There's nothing really comparable. Although
Okay.
I guess there is. I mean, you can make a folded dipole, but that's really kind of a different beast.
And so if you take a quarter wavelength and you put it on top of metal, car rooftop.
Mm-hmm.
The car rooftop is orthogonal to the antenna, then the direction changes. How does that influence the signal?
You actually get a stronger signal. Basically, the signal that would normally have aimed downward is now aiming upward. So basically half of the donut that you would be generating is actually flipped to the top. So it's actually a potential. Now that's only if the ground plane exists forever, which of course it doesn't, right?
And would that induce any interference, or
No.
it's negligible?
No. It basically what it does is it induces currents to flow in the roof of the car at RF frequencies. Pretty cool, right? It actually makes current flow in the roof of the car.
So if you were to mount an antenna, say on the corner of a vehicle, that side that's exposed or not on the vehicle, it essentially is not going to work off that side because it doesn't have a ground plane to work on.
It will not work nearly as well. Yeah, your radiation pattern will not be symmetric. You'll actually have your direction of maximum radiation. Like I used to actually have this. I had a 1995 Dodge Neon with a 13-foot antenna on it, tunable antenna, and it was in the back right corner. And whenever I wanted to work some really distant station, if I was pulled over somewhere, I would sometimes have to turn the car 90 degrees to optimize my signal in the direction of the rest of the car.
So it actually turns it into a directional antenna depending upon the location on the vehicle.
It does, yeah.
So ideally, anytime you mount it, always put it in the center of the roof of the vehicle as best as you can.
That's the rule of thumb, if you can. Now, my antenna was 13 feet long. Most underpasses are 13 feet 2 inches. So by the time the antenna was done, it was already almost scraping every underpass I went under. So let's see. Then there's something called antenna loading.
Can I ask a question real quick?
Yeah.
So how big of a deal is it if you don't do the 95%? Because when you did the 95%, you ended up rounding up from let's say 64.86 feet, 65 feet.
Yep.
Is that big of a deal too? Just rounding up that point.
That little, a little bit of rounding is not a big deal, and here's why. So let's say that you have an antenna, and let's say, okay, we're going to make this antenna, and we're going to draw our frequency chart, and our target frequency is right here. We want our dip in our antenna SWR, which we're going to get to be right there. And we say, okay, well, it actually looks like this. So our antenna is obviously working best at a frequency here's 0, here's infinity. The frequency is too low. If the frequency is too low, what can we do with the antenna?
Shorten it.
We can shorten it. Okay. So you grab your wire cutters, you go snip, snip, snip. You take a little bit off at a time. Okay. What happens if you instead make your antenna and you find that it does this? And the frequency is too high.
You add some nings.
Okay, which is easier, adding stuff or cutting little pieces off?
Cutting stuff.
Always better to make it a little bit too long than too short. Because you can always cut some off. It's really hard to add it back.
Measure twice, cut once.
Oh, it's more than that even. That's true, but always err on the side of making the thing longer than you think it needs to be.
Okay,
and that's why. Very good rule of thumb when it comes to constructing something like this.
So Scott,
yeah,
a length of an antenna, if you're in the 2-meter band, that would cover, if you figure it out for a 2-meter band.
Yep.
How well does that cover the whole band?
So you'll typically find if you, and if you go and like buy an antenna that's cut, let's say it's stainless steel, and they say, you know, trim for minimum SWR, you'll typically just aim for the middle of the band and be done with it. And you know, it's time to take a 5-minute break. And as soon as I get done with the bathroom, I'll pull up an antenna SWR chart for like a commercial mobile antenna, and you'll see what it looks like. All right, 5 minutes, everybody. Okay, so there's a good frequency. There's a good SWR versus frequency curve. That's something that's kind of typical.
Yeah, with ham.
Hey, Scott,
Hey,
are the 5 minutes up?
no, I just happen to be back.
Okay. Just let us know when all the 5 minutes are up.
1 more minute.
Okay.
Oh, Scott, quick question here.
Yeah.
When you're showing the half wavelength dipole antenna, vertically or whatever, you always show a little gap in the middle. Like it's not just one piece of wire or something's connected. It's separated in two halves of some sort. And I guess that's so that a wire will connect to each of those parts. And go down into your transceiver or something to get that signal that the antenna receives amplified in some manner, right? So it actually is in two separate parts.
It's two halves.
Uh-huh.
It is. Now, you can actually and this is something that we haven't discussed yet. It is possible to have a single piece of wire and have two feed points that are separated a distance apart, so that you're able to basically use like a solid or a single piece of wire and feed it using something called a gamma match. And that relies on the fact that the feed point is spaced away from the center. This is actually how you would, for instance, if you have a commercial radio station and it was an AM radio station, if you have a grounded tower, you'd basically have one connection going to here and the other one connecting to it some distance above, so that because you're at a given frequency, it's not actually shorted out, because by the time you start looking at the distances, you're far enough away from ground that you can actually create a voltage there. This is actually known as like a shunt fed tower. It's a different mechanism for feeding energy into an antenna, even if it's a grounded antenna. There's all kinds of cool tricks. Antennas are what's known as a black art, because they often, they follow physics, but the physics is often quite complicated, and there's a lot of ways to do things that a lot of people haven't still even really thought of. There's all kinds of cool tricks. Essentially, antennas are about getting current to flow. Like, you would not think, okay, let's say that we have an antenna that looks like this. So here's a dipole antenna. Right? Two halves of a wire. Now, how about an antenna that looks like this? A solid piece of copper with a hole cut out of it.
Huh.
Where you have a feed point here and a feed point here. A solid piece of copper. And this is empty space. This actually works. This is called a slot antenna. And it relies on the fact that it's a narrow slot, and it essentially can function as a loop. There's so many different kinds of antennas that are out there for so many different purposes that you could literally, if you go down the rabbit hole, spend all your time doing nothing but investigating and modeling and designing and building and testing antennas. There are a lot of people that do that. This is part of the fun.
I had thought immediately about the antenna that's on your automobile that telescopes out.
Yep.
You were talking about changing the length or cutting stuff off.
Okay. We're actually getting to that right now.
Oh.
Somebody mentioned something called a rubber duck.
Yeah, I did.
Okay, a rubber duck antenna. This is a rubber duck antenna, so called because it's flexible and it's rubbery, right? Okay, so we know we're going to do a calculation here. We're going to pick 146 megahertz. Is everybody ready to do some math? 300, F, and lambda. Okay, we have our frequency right there. 300 divided by 146 is 2.05 meters. All right, so 2.05 meters divided by 2. So that's a full wave on 2 meters. A half wave, is 1.025 meters. And we're going to make a quarter wave. A quarter wave is 0.51 meters.
Okay.
Multiplied by 39.36 inches per meter is 20 inches. Okay? Now, we're going to have to multiply that by a factor of 0.95.
Nineteen,
so 95% is 19.1 inches. That is roughly the length of a quarter wave 2-meter antenna. This is what I have on my house. I have an antenna on my house. It's been up there for 5 years. I made it for a total of $5. It's 19 inches of number 12 solid copper connected into an SO239 connector, which basically looks like this. And then I have a radial and a radial and a radial and a radial. Each of these are about 19.5 inches long. And then it's just basically mounted on a piece of PVC. The cable goes down through the PVC. And this is my $5 2-meter vertical antenna. So, the question is, would you believe, to quote Maxwell Smart, that this right here is a quarter wave 2-meter antenna, when I just said that a quarter wave vertical 2-meter antenna is how long? How
19.
long should it be?
19.
This thing is 7 inches long. Why is it 7 inches long?
It's tuned for its operation.
Nope.
Loading coils.
Loading coil. A loading coil is basically a winding of wire that is electrically short. It essentially makes an antenna the right electrical length by shortening its mechanical length. So really, that antenna that I have has roughly 19 inches of wire coiled up in it.
Okay.
The advantage being that now it's flexible. So what do I give up? Well, what is the fundamental thing about an antenna? What does the current at the end have to be?
0.
0. All right. Current at the end has to be 0. Well, this is a quarter wave antenna, which means it's actually half of this, which means that the current is at its most down here. And if I started to draw that wave, it goes like this. But then what happens in here? My peak gets big really fast because it's all short, right? Well, what happens to all the wire that's all coiled up if I have current that's going this way and current that's going this way right next to each other? They tend to cancel each other out. So this really means that this antenna essentially is very, very non-functional down in that region. It does not do a very good job. Why do I care? The question is, I want somebody to tell me, why do I care or not care?
Well, it prohibits your performance.
It reduces your performance drastically. Yeah, okay, that's a reason I do care. Why do I maybe not care?
It makes it super portable.
It makes it very portable. That's true. So that's a trade-off, okay? What's another reason that I do or don't care?
You can switch out the antenna on it very easily.
Yep.
With another longer rubber duck or to an actual antenna on like a house or car.
I can do that. Yep. Because they're threaded antennas. The connectors are threaded. Okay. Now, how about the other question? Well, who am I trying to talk to?
Other people on ham.
Okay.
Or
well, this is a very important question. The question is, am I trying to talk to other people directly? I don't know. If I'm on the ground, like right here, trying to talk to another person directly, and there's terrain in between us, our handheld radios now have to basically overcome all that terrain, which may or may not work very well. If we're using a repeater, that's up here on this tower, do I worry so much about the terrain?
Not if you're going to a tower.
That's right. Okay. So, in other words, the performance of this antenna is measured in something called gain. We're going to be talking about gain probably late today, early tomorrow. And gain is measured in decibels. It's essentially a performance rating of one thing compared to another. Well, as it turns out, I get a lot of gain by using this repeater way up here on top of this mountaintop, right? I can actually take my handheld and I can listen to the space station flying overhead quite easily. It's 200 miles away, and I can hear it very, very well on this antenna. In other words, there's enough gain in that antenna, and it's a fairly lossless path because it's line of sight, that it really doesn't matter. So there are times at which, let's say, I'm just walking down the street and I don't really feel like getting my armpit jabbed by a long antenna, that this antenna is just fine. Now, there was also another company that made something called, believe it or not, a stubby duck. So here's your radio, and here was the antenna. This is a 2-meter antenna, and this is real size. It was 1 inch long. It was 1 inch long. How long should it be electrically? For a quarter wave antenna? It should be 19 inches. It was a 1 inch long stubby duck antenna. Why would you ever use that?
Isn't that the type of antenna that they would have on like kids' super cheap walkie-talkies?
Could be, yeah. But why would you ever use that antenna?
To talk to people that are really close to you.
Really close? Or let's say that you're actually at a repeater site, right? Or within a half a mile of a repeater. And there's so much excess gain that you could be right here using basically this tiny little antenna, and the repeater is over here on top of this tower with so much extra gain that you could be running 1/100th the amount of power that's coming out of it and still be able to use it. So that's why loading can work. And that's known as antenna loading. Okay, a beam antenna is an antenna that concentrates its energy in one direction. So this would be known as a beam. This is actually known as a Yagi, named after one of the two inventors. The other one was Uda. So this is a beam antenna, concentrates its signal in the forward direction. At its core, right here, this is an antenna that looks like this. What does that look like, everybody?
Looks like one of those antennas
Arrow.
that you would get.
No, but this section right here in the middle, that's a half-wave dipole. So you would then make this one, this is known as the reflector, slightly longer, and these are known as directors. Those are slightly shorter. You would typically have one reflector and one or more directors, and they would basically parasitically resonate with the driven element. This is called the driven element, and direct your energy in the forward direction with only a little bit going out in the back. So it basically changes your pattern so that you have a much more concentrated signal in the forward direction. And that's known
Are
as
those
a beam.
on top of the houses?
On top of a house, like a TV antenna, similar. That's actually something called a log periodic, which is a form of a beam antenna. But you'll notice that the pattern, if I were to draw the elements, would look something like this. And the way that this works is that these antenna elements are logarithmically related, so that on any one given frequency, only two of the elements are actually in play. So on another one, it would be like these two. On another frequency, it would be only those two. And what that allows you to do is have a very, very wide bandwidth. So this could be used from like 100 to 1,000 megahertz successfully, but with low gain. So very wide bandwidth and very low gain. And this is
which is fine if you just try to receive from the tower.
Right. If this is for a TV antenna, this is called a log periodic. You can actually build them as transmitting antennas too. And in fact, the military uses these, especially for installation, and actually for high frequency too. You can actually do a high frequency log periodic that covers the entire 3 to 30 megahertz band, or let's say 2 to 40 megahertz band continuously with low gain, but with directivity, because you put it on a tower and it's rotatable. But something like this would potentially have so much aluminum that it would weigh a couple 100 pounds and cost, oh, I don't know, $10,000.
So
But-
on
Yeah.
so on the on the periodic that you drew, only 5 out of 8 are in play.
No, they're all in play, but they're all in play on different frequencies. Like
Okay.
some of them are on, let's say that you pick one frequency. 2 of them are in play and the rest of them are not. Because the other ones are either so long or so short that they're just basically, they don't do anything.
So they're all tied together electrically. They
Yep.
just don't do anything within
Correct.
that.
And the tricky thing is, yeah, they're all actually typically what you'll see is that the way that they're fed is something like this. And then you have another one that goes like this.
So something that I heard with old power cords for like laptops and stuff.
Mm-hmm.
I heard that they used to create radio frequencies. So they put those little boxes.
We're getting to that.
Oh, chokes.
We're getting to that. We're getting to that.
Oh.
Okay. The gain of an antenna is how much better in a particular direction, in the peak direction usually, an antenna performs than some reference antenna. So most antennas are compared. What reference antenna do you think most antennas are compared against?
Dipole.
It would be a half-wave dipole. The half-wave dipole is kind of like the standard antenna. Now, there's also something called an isotropic radiator. And what I'm going to do is draw a dot. And around this dot, I'm going to draw a sphere. And connect all the dots, and here's my sphere. An isotropic radiator is an antenna that transmits a perfectly uniform signal in all directions, or every direction around the sphere, perfectly uniform. This is known as an isotropic radiator, and it does not exist in nature. It physically does not exist. However, this is known as an ultimate reference antenna. So when something is measured in decibels of gain, it can be either measured in dBd or something called dBi, right? Decibels with respect to a dipole is going to typically be a lower number than decibels with respect to this isotropic radiator, because it's an imaginary antenna that doesn't really exist. Some manufacturers will actually specify dBi, but to be totally honest, it's not that easy to compare it against anything. Mathematically, 1 dBd is equal to 2.05 dBi. So so actually 0 decibels with respect to a dipole is actually 2.05 dBi. But you don't have to remember that, but that may come in handy someday. Okay, what's the disadvantage of a rubber duck antenna? The disadvantage of a rubber duck antenna.
Less gain.
Much less efficient, much less gain. Why would you not want to take an antenna and stick it inside your car instead of outside your car?
Because then the metal would be blocking the signal.
Yep, you get a shield. You get shielding from the car. So why would a longer antenna ever work better than a shorter antenna?
More range and more gain.
Yep, more range and more gain. So on a car, I can put a quarter wave antenna. I can also put a 5/8 wave antenna. A 5/8 wave antenna, if I were to draw a current, looks like this. So I actually get a lower radiation pattern than this one. So this one would look like that. This one would look like that. And since most of the people you're trying to talk to are along the ground, a 5/8 wave antenna is a better antenna, except that this is 19 inches long and this one is 45 inches long. So if you have a sport utility vehicle and you park a car in a garage, which one do you pick?
The 19.
You pick the 19.
So could someone make a rubber duck out of that?
The problem is if it's a mobile vehicle, you know, if it's a car, as soon as you start moving, the antenna is going to bend. In which case, the pattern is going to be all messed up anyway. All right, guess what we're up to, everybody? We're going all the way back to the beginning. We're going to electronics. And we're going to start doing Ohm's law. Okay, Ohm's law, named after Georg Simon Ohm. You'll find that most of the units and laws that we're going to talk about were created, developed, discovered hundreds of years ago by scientists, mathematicians, engineers. So here we go. We're going to draw. Our first thing that we're going to draw is a battery, plus and minus. And then we're going to draw a resistor, and then we're going to complete the circuit. All right, so this is our battery. Our battery has a voltage E, which is electrical impulse or electromotive force. It's measured in volts. So again, E stands for electromotive force, which is the ability to move electrons. Okay, this is a resistor. Its job is to see a voltage that is being applied to it, like this, and say, I'm going to fight the flow of electrons being generated by that voltage. So, the higher the resistance of something, the better its ability to fight the flow of electrons, to fight back. That's resistance is measured in ohms. The little symbol is the little letter omega. And the movement of current is I. And it's measured in amps, short for amperes. And this comes from French. This is impulse. But really it's current. It's the movement of electrons past a certain point on a wire or in space or anywhere. So electromotive force, that's measured in volts. Current, that's measured in amps. And resistance, that's measured in ohms. Okay, Ohm's law. E equals I times R. Voltage is equal to current times resistance. Now, I also draw it like this, EIR. I've also seen it done in a triangle. This works the same way. If you can't remember which, you can always draw this. If you say, okay, well, I'm going to take my very first circuit, which comes from the word circle. Current flows in this direction. By definition, current flows out of the positive and into the negative side of the battery. And if I have a voltage of, let's say, 10 volts, and I have a resistance of 10 ohms, well, I don't know my current. E divided by R. I is equal to E over R. Is equal to 10 over 10 is equal to 1. And the unit is amps. So that's my current, 1 ampere. So, does anybody know how many electrons flowing in 1 second an amp is?
A watt?
It's a lot. 1 amp is about 10 to the 19th power electrons per second. Electrons are really, really small, but there are a lot of them. So that's 1 amp is known as 1 coulomb per second. A coulomb is essentially a bundle of electrons. It's roughly 10 to the 19th electrons. It's a lot of electrons. Okay, so now we've done Ohm's law. So let's do some Ohm's law stuff. All right, so we're going to draw another circuit. Here we go. Here's our battery. Excuse me, I'm going to say 100 volts. And this is our resistor. We're going to say this is 10 ohms. And our current flows this way. Okay, by Ohm's law, E is equal to I times R. We can do E, I, R again, like that. Well, clearly we don't know the current. So we have I is equal to E divided by R is equal to 100 divided by 10 is equal to 10 amps. Okay, now we have another part of Ohm's law. Everybody ready for the second half? Here's the second half. P is equal to I times E. And P is power, and this is measured in watts. And the cool thing about power and energy is that essentially a watt is a unit of energy per second. It's called a joule per second. The nice thing about energy is that energy is conserved. It can neither be created nor destroyed. It just changes form. It even follows the E equals mc squared. So what's nice about this is that we can now take our power and our energy, and we can convert electrical energy to mechanical energy, or chemical energy, or rotational energy, or just about anything. We can convert RF energy into heat. We can convert heat into chemical energy, and so on and so forth. So what we're going to say now is, since we have this formula that says P is equal to I times E, we're going to say, how much power is this resistor going to be dissipating as heat? Well, we know that our current is no longer unknown. We know that our current is equal to 10 amps. And we know that our resistor is going to be 10 ohms because we just drew it that way. And we have P equals I times E, and E equals I times R. Well, let's look at this here. What do we have? We have I and R. Okay, well, if we know that P is equal to I times E and E equals I times R, we're going to substitute that in, and we get P equals I times R, or I squared R, is equal to 10 times 10 times 10 ohms is 1,000 watts. So, what did we just make, everybody? What did we just build?
1,000-watt heater.
That is a 1,000-watt space heater. That's exactly right. That is an electrical resistance space heater. Now, that is if we did this correctly. Let's say that that resistor that we built in there is capable of dissipating, because it's made of ceramic, it's capable of dissipating 2,000 watts. Well, that's great. We just built a space heater. What if that resistor is capable of dissipating, let's say, 10 watts? What will happen to the resistor?
Uh-oh.
You let the smoke out.
The first thing that'll happen is that it'll turn slightly red, and then it will Let's go through the colors, everybody. It'll turn red, then it'll turn orange, then it'll turn yellow, and then it'll probably burst into flames because it's going to be really, really hot. So, not a good idea to do that. So, let's say that we've done everything right and we've built our circuit so that, okay, we have a resistor that can dissipate 1200 watts. And we're dissipating 1000 watts through it. So, everything is hunky-dory, just fine, right? Okay, but let's say something bad happens and our resistor develops a partial short circuit and now it's only 5 ohms. Let's say part of it shorted out, so we're only now 5 ohms. Okay.
We'll start heating up.
Well, so let's do our calculations again, right? So we don't know what our current is. All we know is that we're still running the same voltage. And, well, okay, let's do our calculations all over again because all this stuff goes away. So the first calculation, we have to figure out what the current's going to be. So E equals IR. E, I, R. Just like that again. We don't know our current. We know this is 100 volts, and we know this is 5. So I is equal to 100 divided by 5, which is now 20 amps.
20.
Okay. Now we're going to do our power calculation again. P equals I times E. P, I, E, the same way. We don't know our power. We have I times E. That'll work too. P equals I times E is equal to 20 amps times 100 volts is now how much power? 2000 watts. Okay. Well, on top of that, we just took that resistor and we actually shorted out half of it. So maybe it's not even good for 1200 watts anymore. So what's going to happen to that resistor? Let's say it's only now rated for 1000 watts. And we're now putting 2000 watts of power through it. What's going to happen?
Same thing as what happened
fuse out.
before. It would heat up and
It would
probably
go,
catch.
yes, potentially burning your house down. So,
And or exploding. Hopefully not.
so what we do is we now can say, okay, how much current can we really have in here and still have everything be okay? You remember what it was before? It was 10 amps, right? So we had a circuit that at 10 amps, everything was just fine. And if we only had 10 amps in here right now, we would probably still I squared R, let's see, 100 times 5, that'd be 500 watts. We would still be fine. So the problem is that there's now too much current. So if 10 amps is okay and 20 amps is no good, what we can do is we can throw a device in here that is defined as a sacrificial element that will kill itself and thereby protecting your house if there's too much current. Anybody know what this is called?
A breaker.
A fuse.
A circuit breaker? Or, they're both right. So this could be a circuit breaker or a fuse. And essentially what that is a device that is designed to heat up when the current gets too high. This is an overcurrent protective device that's designed to protect your circuit. And virtually everything that you buy that runs off of, that plugs in, will have a fuse built in. You also have fuses or circuit breakers built into your home to protect all the wiring and to protect your outlets. Thus, ideally, to keep your house from burning down.
Isn't there like a breaker box or fuse box?
Yep. You're going to have a breaker panel somewhere in your garage or basement or something.
Or somewhere in a closet.
Okay. Here we go with the
Even
next one.
the greatest things that protect it still has some flaws. So it's still able to catch on fire if the circuit breaker or the fuse breaks.
Well, it could potentially arc.
Mm-hmm. Or just the whole entire like wiring just like snaps.
Well, that's what happens when the breaker trips.
Mm-hmm.
Yeah.
So if one trips, you have to figure out what tripped it and fix that.
Right.
Or just replace it if it was just bad fuse.
Yeah.
Or if you're not able to fix it at all.
Well, then you'd have to replace it. Okay.
And if they can't fix it,
well, everything can be fixed one way or another. Okay, here we go. Next. What is the name for current that flows only in one direction? So we're just gonna breach this topic right now and just get it over with. All right. So this is a battery. It has a plus and a minus. Here's a resistor, like this, and here's my E and here's my R. Okay. By convention, current flows out of the plus and back into the minus. All right. But what did we just say a couple of minutes ago that current is? The flow of what?
Electrons.
Electrons. What charge do electrons have?
Minus.
Negative.
A negative charge. That's right. Hey, Ruchi, are you still here?
Yes.
Can you explain who made the mistake? Because it happened a long time ago, and why the mistake remained the mistake.
I'm sorry, which mistake?
The fact that current is actually the flow of electrons, and they managed to get it backwards. Do you remember exactly how that happened?
I do not remember that.
Okay. I don't remember either, but the mistake was made. Mistakes were made a long time ago. And this was before I think anyone realized that electrons were negative. They just knew that there was a positive and negative terminal on a battery. And now that we know, no, I don't think it was Ben Franklin. I think it was probably around the time of like Michael Faraday or... So basically we know that electrons really flow out of the negative terminal, right? The negatives flow this way, but by definition, current is positive.
Well, there was something with the flow of protons, which doesn't really exist. And to keep the numbers right, I think, to make sure everything's end up being positive for sign convention.
Okay, what was it?
Think of electrons.
The flow of what? What was it called?
The protons, just like the positive, but they don't really flow. They're static in the wires.
Okay, so basically just to make the math add up. Okay. Well, anyway, so that's the last time you're going to hear me say that the current really flows out of the negative. For the sake of all of engineering school that I went through and all of physics and everything else that everyone else ever studied, current flows out of the negative and into the positive. Or sorry, the electrons flow out of the negative and into the positive, and the current flows out of the positive and around back to the negative. And we also define, if we're doing a negative, if we use something called a ground, this is defined as 0 volts. That's our zero potential point. So very often that is our reference point for 0 volts in a circuit. Doesn't have to be, but it usually is. Okay, so with this particular circuit, we have something called DC, direct current. If we were to draw a graph of what the current would look like, we would have negative and positive. And in this particular case, our current would always be positive for time, for all of time. Okay, now if we were to switch this and do this and get rid of the plus and minus signs and do this with it and make this sine wavy looking thing inside it, what we would end up having is that sometimes we would have a plus here and a minus here, and for the rest of the time those would reverse and we'd have a plus here and a minus here. What that means is that when we look at a current, through a particular point, sometimes it'll be plus and sometimes it'll be minus. And if we have a sine wave driving it, our current will be in the form of a sine wave, which means that sometimes we have a positive current going this way, but sometimes we have a negative current, which would be going this way, and this would be known as alternating current. Okay, now, the important thing to note here is that direct current is really boring but very stable. Alternating current is very unstable. It goes back and forth. It always changes state. It has a given frequency because it switches in a period of time. In our wall voltage, this is known as 60 hertz. It flips every, it does one full cycle where it goes plus minus every roughly 16 milliseconds, or 60 hertz. Now, the other thing is that radio frequency energy, let's say that we were doing 3 megahertz. That is also a sine wave, just like that. That generates alternating current. So DC is very, very stable and very, very boring. AC, or alternating current, is very unstable, but it can be of an infinite number of frequencies and is thus very, very interesting, right? Without AC, this class would not exist. It would be very dull. Okay, the number of times per second that an AC current makes a complete cycle is known as its frequency. In the United States, it's 60 hertz coming out of your wall. Its voltage, if you were to stick your meter into the wall, is known as 120 volts AC. Now, this is not exactly true. What you would really find is that you would have, if you were to actually take a picture of it with an oscilloscope, you would find that your peak was about 170 volts and your negative peak was about negative 170. And that is because this voltage AC, this is actually something known as RMS, which is root mean square. And what root mean square is the equivalent power delivery capability of a voltage waveform. So, in other words, this voltage waveform would produce as much power as a 120 volts DC signal. And that's because at this point and at this point, it's actually the voltage squared. We can actually go through and say P equals I times E, and then we could do E equals I times R, and we could substitute a bunch of things in, and we could say power is equal to E squared divided by R, which it actually is. So it turns out that the power is actually proportional to the square of the voltage. So it doesn't matter if the voltage is plus or minus, it goes up here. It goes positive. So the power always looks like this. But it's not uniform. So essentially the time average, this would generate the same as about 120 volts DC, and that's known as 120 volts AC RMS. So anyway, just a little interesting thing to note there. Let's talk about conductors and insulators. What makes a conductor is that it has the ability to allow electrons to flow easily through it. So copper, aluminum, silver, gold, they're all pretty good conductors. Gold is really, really useful because it also doesn't tarnish, which means that even if it's very, very slow to oxidize, which means that its surface stays nice and clean. Aluminum is actually a really good conductor, except has anyone ever worked with aluminum? And know why it might not be a very good conductor to use?
Aluminum can melt very, very easily.
Yeah, but
especially when it's thin.
But we're not talking about about melting.
It expands and contracts too much.
Actually, that's a little bit of it. How about if you have a piece of nice, clean aluminum? How long does it stay clean?
It oxidizes.
It oxidizes
Nah.
really fast.
Oh.
It's very reactive, and it forms aluminum oxide. And aluminum oxide is a very, very poor conductor. So basically what you end up with, if you have two pieces of aluminum that you go like this and you tie them together using something, if they are not completely sealed against the air, they'll oxidize, and they won't be a very good won't be a very good connection anymore. And then you can get hot spots and arcing, and like happened in New Jersey in the 1970s, you burned down a bunch of houses because you decided you were going to use aluminum wiring but didn't really know what you were doing. That actually happened. A whole bunch of houses in New Jersey burned down because of that. It was cheaper. There's no reason it can't work, but it has to be done properly. A good electrical insulator, very often electrical insulators are good heat insulators as well. Not always, but sometimes. A good electrical insulator has the ability to not allow electrons to pass. So gold, paper, mica is a really good one, you know, like the rock. Certain kinds of plastic are really good at it. Okay, let's see. We just did Ohm's law. We're going to shoot past Ohm's law into series and parallel circuits. Okay, series and parallel. So if I take this battery and I go like this, and then I go like this, if you think about water flowing down through a stream, the current is the water. It encounters this first resistor, and then it encounters the second resistor. So the total of the resistance that it encounters is the sum of the two resistances. Okay, so now that is known as series resistance. Two resistors in series simply add together. Okay, so now we're going to take this circuit and we're going to modify it, and we're going to do this. And we're going to imagine we have our battery and our current flowing, and we have two different paths for that current to flow. So, which way does water flow when it gets to a place a choice?
Down.
Goes to the easier one.
Yep, the path of least resistance. Well, what do you know? Path of least resistance. These are literally resistors, so it'll follow the path of least resistance. So if R1 is, let's say, 1 ohm and R2 is 10 ohms, most of your current is going to go through R1. Mm-hmm. If this is 100 ohms and R2 is 10 ohms, most of your current's going to go through R2. I can keep going with this, and I can make this R3, and so on and so forth, and I can add a whole bunch of them. And there's a formula for doing this. And for two resistors, it is R1, R2 over R1 plus R2. And that's R total. So notice it's not just as simple as adding things together. The easy way to do this, or the easy way to look at this, let's say they're exactly the same. If I have two resistors that are exactly the same in parallel, I'll have 10 times 10 over 10 plus 10 is equal to 5. So that will be cut in half. So basically, two identical resistors in parallel will give you will basically give you half. So let's look at this in the extreme. So let's say that I have one resistor of, let's say, 1 ohm, and the other resistor of this many ohms. What is the approximate total resistance of this circuit?
Just 1 ohm.
Yeah, it's about 1 ohm. It's about 1 ohm. For all intents and purposes, this resistance is so big that this is very similar to just drawing it like that. Let me draw it the right way. There. Call it infinity. That's an open circuit. It's like it's not even there. So the net result is essentially it becomes almost equivalent to an open circuit, which is an infinite resistance, which gives you a total circuit resistance of 1 ohm, or roughly 1 ohm. Okay, so let us say that if we now take a series circuit and we do this, what can you say about both of these resistors? Will they experience the same or different currents?
Same.
The same. They have to be the same, because every electron that's here has to push through to here, to here, to here. The resistors have to experience the same currents. Now, if that's true, and we have I right here, if we were to measure the voltage across each of these, we would have Ohm's law, E is equal to IR. So E1 is equal to I1R1, E2 is equal to I2 IR2, and we would see that the voltage measured across this resistor is going to be different, probably, from the voltage measured across this resistor, because the currents are the same and the resistances are different. They're going to experience different voltages. So now let's look at the classic.
Scott,
Yeah.
when you say R1, R2, one is, I'm not clear whether you're just saying this is the first one, this is the second one,
Yep.
or you're saying they
Nope.
have different values.
Well, I'm just saying whatever R1 is, I can say this is 3 ohms, and I can say R2 is 4 ohms.
So, but exactly, they don't they don't have the same value. They have different values.
They might, but they don't have to. It's just whatever they happen to be. In other words, there's no guarantee that they're going to be the same. There's no guarantee at all that they're going to be the same. They could be.
But is there a difference in what the current is going to be when it flows on past both of those?
No.
If they're the same or different.
In other words, whatever the end result is, the same current has to go through both of them. It can't, branch off somewhere and go somewhere else. There's nowhere else for it to go.
But the value of the current.
The value of the current potentially will change.
That's my question.
Yeah.
So like if I have an extension cord that's, 800 feet long, the drill on the end of it won't work.
That's right. That's exactly right.
The wire itself is using up so much of the current, there's nothing left when I'm 800 feet out.
Well, actually, what's happening is that the resistance of the power of the extension cord is using up so much of the voltage.
Okay. Yeah. All right.
Right. Because in that case, I could say, okay, well, R1 is my extension cord, and we could say that this is 400 ohms, and R2 is 1 ohm. The total is 401 ohms. You just add them together, and you can then do E equals I times R and figure out what the overall current would be, and then use that current right there, and you would see that, let's say this is 120 volts. You would basically have about a quarter of a volt over here, and you'd have about 120 volts being burned up in the power cord.
Okay.
So what would the power cord be doing at that point?
Well, the power is being diminished or used up.
Where's the power going?
Heat.
Heat.
It has to come out as heat. Energy can neither be created nor destroyed. It can only change form.
Okay, well, maybe it's heating up.
Yeah, it's heating up the power cord. That actually has a name. If you've ever seen like a cord that you throw on your roof, if you live in a cold climate, like a really long power cord, a very low resistance but really long power cord that you snake on your roof so it keeps it from freezing.
Ice melt.
Yeah, it's an ice melter. That's exactly what it is.
Okay. I used to have one of those under my trailer out in the woods.
There you
And
go.
that's what kept the plumbing under the trailer from freezing.
It's exactly what that is. Okay, it's just that that's a calibrated value. That's all. Okay, so let's see. So now we're going to redraw this circuit, and we're going to draw it as a parallel circuit, like that. And now we have R1 and R2. And what do we know if we have a voltage E across this point? Draw our ground. What's the voltage across this resistor? E. And the voltage across this resistor is also E. And we now have Ohm's law we can do right here, and Ohm's law we can do right here. And if the E's are exactly the same, what's going to happen to the currents, I1 and I2? They are going to now be proportional to, or inversely proportional to, the resistance, because E is equal to I times R. I is equal to E divided by R. So we would have the same voltage and different currents. So this would actually be kind of like a current dividing circuit. If I were to draw that other circuit again and do it like this, where I had E and then ER1 and ER2, I would actually be able to divide my voltages. This would be known as a voltage dividing circuit. So this right here is a current dividing circuit, and this right here is a voltage dividing circuit. So does anyone recognize this circuit from if I were to draw something that looked like this? A whole bunch of resistors. And then these resistors are very special in that they light up. And if something were to happen and this one of those resistors were to, let's say, burn up and stop working, and all the other lights went out, what is this known as?
Christmas tree lights.
That is your standard Christmas tree lighting. That's right. It's because they're all in series, and thus if you lose one of the bulbs, you lose the entire current path for all of them. Whereas if you do it like this is difficult to do in a string of Christmas tree lights, but it's really easy to do in your house. Can you imagine if you had a light bulb that you pulled the light bulb out and all your lights went off? That's why we don't do it that way. That's why we do it like this instead. So Christmas tree lights are wired in series. House lighting, wired in parallel. Okay, so let's see. We've done DC power. All right, we're into math. Yay! All right, any questions before we move?
Well, I just have a comment that that I can make parallel in hydraulics. We have something pretty similar in that voltage is equal to like water pressure, for example. The current is equal to the flow through the pipe, and the resistance is the friction in the pipe.
Mm-hmm.
And there's a lot of parallels between these things. Let's say, and we also had an example of, let's say if you had a reservoir on a hill and a pipe coming down, if you had a small enough pipe with enough resistance that even if the pipe was open at both ends, water wouldn't come out.
Mm-hmm.
Because the resistance, it's a similar situation in a lot of ways.
Yeah, well, it's
and
also
for
It's very
for,
similar to heat flow and thermodynamics.
Yeah, it's helpful for chemistry people to understand electricity kind of concepts. So I just wanted to make that comment that we had that kind of examples way back in hydraulics.
Cool. Other questions or comments? All right. So if anyone's
you said that we would get to the power cable thing on how it created
Yep.
radio waves.
Yep.
So how does that work?
We're getting there.
Oh, okay.
Patience. Okay, here we go. Math for electronics and conversion of units. We have to do a little bit on this first. Okay, so we are on page 12 of the book. And so there are a bunch of units listed. So what we need to do a little bit is powers of 10. So if I draw this thing and this notation, which is 10 to the third power, this is shorthand notation for 10 times 10 times 10. This is the other part of it. 10 to the minus third power is 1 divided by 10 times 10 times 10. All right, we just need to get that out of the way. So that's our scientific notation for exponents. Right? So we have our base and we have exponent. Right? That just means that our base is multiplied by itself the exponent number of times. So if we have 10 to the fourth power, we have 10 times 10 times 10 times 10 is 10,000. Now, the inverse of this, the inverse function, is something called a logarithm, which is a related function. It's kind of like the opposite of doing an exponent. So, this is basically to say, what is the log, for instance, base 10 of 10,000, which is the number to which 10 has to be raised in order to get the value 10,000. So 10 to the what, this basically means 10 to the what is 10,000?
4.
And the answer would be 4. So the log base 10 of 10,000 would be 4. So those are just a couple of things that we need to cover in order for any of this to make sense. Okay, so now that we have that, we're going to look at prefixes and how they work with exponents. So for instance, the big letter G is giga. Everyone's used to this, gigabytes, gigahertz. So this is 10 to the 9th power, which can also be written as 1,000,000,000,000. And we can also write mega and kilo. And then on the small side, because small things exist also, we can do little letter m, which is milli, and micro, and nano, like nanobots, and pico. Mega is 10 to the 6th, kilo is 10 to the 3rd, milli is 10 to the minus 3rd, micro is 10 to the minus 6th, which is a millionth, nano is 10 to the minus 9th, pico is 10 to the minus 12th power. So why did we bother to write all this stuff out? The reason being that if we were to write 1 picofarad, which is a capacitor, that would be 0.0000000000001 farad. Or we could just take all those decimal points and replace it with this little letter P. The same way, we could take this many hertz and replace all those zeros with the big letter G and say this is 1 gigahertz. We can also convert from one to another. For instance, to say that 2.3 gigahertz is how many megahertz? Well, we can do it a couple of different ways. 23. We can look at this and say that giga compared to mega is a factor of 1,000. So obviously by doing that, we need an extra 1,000 thrown in there. So it's 2.3 times 1,000 is 2,300 megahertz, which we know to be true. That falls in the UHF band. The other way we can do this, if we didn't want to go that route, is we could do 2.3 gigahertz. We could say that's 2.3 times 1,000,000,000 hertz. And then we could separate this out and say it's 2.3 times 1,000 times 1, 2, 3, 4, 5, 6, 7. That's a million. Well, we know that's mega. And now we know it's 2,300 megahertz. We group that, that's 2,300, and then the rest of it becomes megahertz. So, all right, so now we can actually do things with it. So 1.5 amperes into milliamps. So a milli is 0.001. So we can now say that this is 1.5. We can multiply this arbitrarily by 1,000 and by 0.001, realizing that that's just another way to write the number 1. You can always multiply something by the number 1 and come up right where we started, and then group them differently. So that's 1,500 times 0.001 amps is 1,500 milliamps. And that's how we go through and change units around. So 500 milliwatts, we know that milli is 0.001. So that's 500 times 0.001 watts is equal to 1/2 of a watt. The next thing we're going to do is this thing called decibels. All right, so now, just a minute ago, remember we were talking about powers of 10. So let's say 10 to the 6th power. That can also be written as 10 times 10 times 10 times 10 times 10 times 10 equals 1 million. Okay, so now let's say that we wanted to compare this number, which represents something. Don't know exactly what, doesn't really matter, with something else which has a value of 1. We want to know how many orders of magnitude bigger a million is than 1. We have something called a bell, which is log base 10 of thing 1, or sorry, we'll go thing 2 divided by thing 1. So that's a way of comparing logarithmically or exponentially how many times bigger, how much bigger thing 2 is than thing 1. So we can write this as log base 10 of a million divided by 1 is log base 10 of a million. Okay, so now what we want to know is that log again, that means to what power does 10 have to be raised to get a million?
6.
That would be 6. So that would be 6 bells. Okay, has anyone ever heard of the bell?
No.
Oh, okay. It turned out that the bell was not a very big unit and it wasn't very popular because you ended up with a lot of decimal points. So what we did is we took that thing and we made it something called a decibel. Hopefully people have heard of that one. And we took that bell and multiplied it by 10. So the new formula is 10 log base 10 of thing 2 over thing 1. And that is known as a decibel. And what that did is it basically took the bell and multiplied it by a factor of 10. So that would then be 60 decibels, which is really the same as 6 bells. It's just that it's a bigger number that makes a little more sense. So what this allows us to do is kind of give an exponential feel to how much bigger something is than something else without carrying around all those little zeros. So for instance, if we were to say that we started out with 1 watt of power at our transmitter, and at the other end we had 0.00000000001 watt. Right? Well, you could say that most of your power is lost, which is true. So this is your P1, this is your P2. Okay, let's figure out how many decibels are lost here. So dB is equal to 10 log base 10 of 0.00000000001 over 1. Okay, well, so the question then is this log base 10 of that. That means 10 has to be raised to what power to get 0.00000000001. Well, we can figure this out. Let's take our little decimal point and start moving it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. Okay, so that means we had to take and move the decimal point 12 times to the right, which means that it's 10 to the minus 12th is equal to that. By convention, that means we had to move it 12 decimal points over. So what that means is now we have decibels is equal to 10 times minus 12. It's minus 120 dB. What's kind of cool about decibels is that you can add decibels around. You can add them to things when you're solving problems. So let's say that I now have a transmitter which has 1 milliwatt of transmit output power, goes into an amplifier that has 20 dB of gain, and this goes through a feed line which has negative 6 dB of loss, and then out to an antenna which has 10 dB of gain. It then travels through space, which has a loss of minus 160 dB, to another antenna that has a gain of 10 dB. Perfect cable down to a receiver, which has a sensitivity of minus 120 dBm. Okay, so dBm, that's actually compared to a milliwatt, so there's our baseline. So let's just go around the circle. Let's follow the path. Plus 20, and then how about right here? Minus 6. Plus 10, minus 160, plus 10, and then down to the end. So we basically start at 0, and we go plus 20, minus 6, plus 10, minus 160, plus 10, and we end up with 20, 30, 40, 34, minus 1, minus 124 dBm. Well, does anyone notice a problem? That was the lowest it could be and still work. What did we just end up with?
Oh, even lower.
Uh-oh, we're a little too low. All right, how can we fix this?
Increase gain.
Where do we pick some places?
Increase the gain.
Amp or the antenna.
Yeah, we could increase the gain of the amp. We could make that 25 dB. Or see this 6 dB loss? We could replace that cable with something that was better. We could put a bigger antenna up here or a bigger antenna right there, which has a little more gain. So let's replace this 20. Let's replace this with 25 dB. Well, guess what? We're now at negative 119, and we went from not hearing anything to all of a sudden hearing something, and everything works again. Has anyone ever had the cable guy come out because your cable was not working right? This is what your cable guy does. This is exactly what the cable guy does with the cable system when your cable is not working properly. It could be that that amplifier, which is literally an inline amplifier, needs to be a little bit stronger, or maybe it's not working right, or maybe that cable, has the cable guy ever taken out a piece of cable and replaced it at your house? Happened to me. That's why. Because your cable is lossy and all of a sudden your signal's not working anymore. It could also be that the transmitter is not working properly, out at the cable box on the corner. That's a small system. It's an enclosed system, but the basic math is exactly the same. So let's take a look at a couple of things that you need to know with regard to decibels. There's really only two of them. 3 decibels is about equal to 2 times. The corollary is that minus 3 dB is about equal to a half. The other one is that 10 decibels is exactly equal to 10 times. And negative 10 decibels is exactly equal to 1/10. These are the only things that you need to know for your exam, and to be totally honest, these are really the only things that you really need to know to solve pretty much anything within an order of magnitude with regard to decibels. Because let's say an antenna is 6 dB, how would you break that up into threes, everybody?
3 plus 3.
3 and 3. And every time you use 3 dB, how many times do you multiply?
Doubling.
Doubling. So 3 and 3 decibels is the same as 2 times 2, which is 4 times. How about if somebody said your antenna gain is 9 dB? How would you break that up?
9 plus 9.
3 plus 3 plus 3.
3 plus 3 plus 3, which is the same as 2 times 2 times 2, which is roughly equal to 8 times. Okay, how about if somebody said that your gain was 13 dB? How would you break that up into things that you know?
10 and 3.
10 and 3. And what happens when you have a 10?
10 times.
10
10
times.
times.
And how about when you
Have a 3.
the 3?
2 times.
Double.
20 times. That's it. That is how, those are the only things that I even remember, even for work. There's other things I can always calculate, but this actually really works. Let's say that you have a gain of 36 dB. What would that be?
10 plus 10 plus 10.
10 plus
3
10 plus 10
3.
plus 3 plus 3. So that's 10 times 10 times 10 times 2 times 2 is 1,000, 4,000 times. That's it. It's quick and easy and it makes a lot of sense. It's very easy to remember. Okay. So now we're into resistors, capacitance, inductors, inductance, and stuff like that. Okay. Everybody want to take a 5-minute break?
Yeah.
Yes.
Yeah, okay, good.
Sure.
I could stand it myself.
Can I ask you a question real quick? Is it too late?
Hey, Rusty, how hot is it there today?
I don't know. Let me look. It's hot. It says it's just 97, but it feels like 102.
You know, it was 48 degrees here this morning.
Oh, shut up. I want to be in the Ozarks in the mountains, but I can't seem to get out of my house and get moved. I have a question. My ADD is off the chart. I'm having trouble focusing terrible. And with all the algebra and everything else, you like totally lost me. On the last thing that you did, you had the 36 dB, and then you did the 10 times 10 times 10, or plus 10 plus 10 plus 10, and then the 3 plus 3.
Yep.
But then you did the 10, and you did minus 2 and minus 2. You lost me on that.
Oh, times 2.
It was times 2?
Uh-huh.
Okay. So 2 times 2 is 4.
Yep. And then times the 1,000 that you had, because it's 10 times 10 times 10. So 36 dB is a gain of 4,000 times.
See, you're losing me on that.
Well, you just have to break it down. I mean, there's only 2 things you really need to know.
Okay.
10 dB is 10 times.
Okay.
And 3 dB is 2 times.
Okay.
So just break this down. That's 10 plus 10 plus 10 plus 3 plus 3. So every time you add a 10, you multiply by it, that would be multiplied by 10.
Okay.
I mean, I could make this, 76 dB. Doesn't matter to me. I could do, that would be 10 plus 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 3 plus 3. And I could do it and say that's 10 times 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 2 times 2. So that would be 10 million, be 40 million.
So the first statement is breaking out your 76 dB. So to get 76 dB, it's just a placeholder for you to figure out how many 10s you need and how many 2s you need.
So really, decibels is a wonderful shorthand tool, because I could say that my gain is 76 dB, or I could say my gain is 40 million times. 76 dB is a much easier way to say it.
So start reading it.
Okay, so what would the likely be question on the test?
They're all in there.
Okay.
If you look at page 14.
Page 14?
There's only 3 of them.
Okay.
There's only 3 that it could be.
Okay.
But this is where it actually becomes useful in the fact that, you're not just working for this test. This is what it's actually useful for.
Okay. I mean, you just lost me on all the all the numbers and the algebra. It's been so long since I had any of that stuff or had to use it or.
Well, here's the other thing though. Let's say you start looking at antennas. So I'm gonna pop this up on the screen. Here. Okay, so we're gonna look at Cushcraft 13B2. Here's a Cushcraft 13B2. Notice how it's rated. Let's look at it. Cushcraft 13B2. It's a Yagi antenna. And let's look at the description. And why isn't it? Videos, product manuals. Download product manual. Okay, here we go. Does everybody see that? What does it say? Forward gain. dBd, decibels compared to a dipole. Can everybody see that?
Yeah.
Okay, how many dBd?
15.8.
15.8. Okay, so what we're going to do is we're just going to do some simple mathematics. And we're going to go over to here and say we're going to call that 16 dB. All right, how would you break that down?
10, 3, 3.
10 and 3 and 3. Okay, what is the 10 decibels give you?
10 times.
Yep. And what does each 3 give you?
Double.
2 and 2.
Yep. So 10 times 2 times 2 is
40.
40 dB. Or sorry, 40 times. Okay, now where this is really important is, let's say that you have your transmitter right here, and you feed it through a cable that has no loss into your brand new 13B2 antenna. And your transmitter is 10 watts. What will the effective radiated power in the forward direction be? Well, you're putting 10 watts into it. What will it be? What will it appear like?
400.
It'll look like 400 watts ERP. Because you just said it's 40 times. I mean, that's where it really comes into play. So you have 2 choices. If you want to run 400 watts effective radiated power, you can put up a vertical and run 400 watts into it, or you can use a 10-watt radio and use this big antenna and have it in that direction and then be able to rotate it in the direction you want. I'm sure everybody else would be very appreciative if you went with that path.
So Scott,
Yep.
our licenses are based on our radiated wattage, or
No, they're not.
transmission?
No, they're not. They're
Okay.
radiated
Cool.
on your RF power.
Wait.
Not
Okay.
not your effective radiated power. They're like you're
Okay.
you're allowed to run 1500 watts into whatever antenna you see fit, unless there's something saying you can't.
Okay, so it's
Awesome.
based on the transmitter, not the
Correct.
gain. Okay.
Right.
Okay.
If you were to stuff 1500 watts out of your transmitter through that antenna,
Yep.
you're going to have a lot of outbound power.
You know what? I've done that. We actually did a VHF contest when I was in Maryland, and we had a kilowatt transmitter and a 13B2 antenna. And so that was, 40,000 watts ERP. And it worked very well. It worked really well. We made a lot of contacts with that thing. It worked remarkably well. Okay, next. Here we go.
So
next.
quick question, Scott.
Yes.
Sorry.
Yeah.
So that gain is both ways, isn't it?
Yes. Gain
Okay.
Gain works in both directions.
Okay.
It's receive and transmit gain. Antennas have something called reciprocity, which is that your transmit and receive patterns are identical. Okay, let's see. DC circuit, an element that opposes flow of DC or direct current, is known as a resistor. A resistor has resistance. Okay, now, something that has a variable resistance would look like this. Potentially it could look like this. Those would be known as a potentiometer or a pot. And they have variable resistance. Those are all forms of resistors. Okay, the next thing is that we're going to draw 2 parallel plates together. And we're going to hook this up to a battery. Okay. So if I were to do this, what would happen to all the plus charges? They would flow over to here. The negative charges would flow over to here. Okay, now, what happens if I disconnect this battery completely? Where do those charges go?
You stay there.
They stay there. Basically, what I've done is I now have these 2 metal plates, which are separated by a dielectric, which could be air, it could be plastic, some other insulating thing. And what I've done is I've charged up the 2 plates. This is known as a capacitor. A capacitor has the capacity to store energy in an electric field. Each of these pairs of pluses and minuses, they desperately want to get together. But the space is not letting them do so. So that tension, that energy, that force that is holding them, that they're trying to pull together with, is being resisted by the mechanics of that device. So this device basically stores energy in an electric field. Now, if I were to take this and suddenly switch the battery and go like this, what would happen is the pluses would flow this way and the negatives would flow this way until it was completely empty. And then, if I left it there long enough, this would be my new plus, and this would be my new minus. And now, if I were to switch this again, such that this was my new plus, and this was my new minus, eventually everything would clear out, and eventually it would fill again with new charges that were just like the old charges, and I'd have pluses over here and minuses over here. Okay, so now, what is that known as if I switch my battery voltage back and forth and back and forth and back and forth? That has a name.
AC.
That is known as AC. Okay, so let's say that I didn't know what was on the other side of this magic wall. All I knew is that whatever I connected to, if I switch my voltage back and forth, I'm going to draw an AC circuit, it flows. It doesn't seem to make a difference. There's this magic wall. So what does it look like if when I switch voltage back and forth, the current flows? I could simulate that by saying that this is a short circuit. So to AC, a capacitor looks like a short circuit. Now, to DC, what happens is that the capacitor charges up, and once it's charged up, can you stuff anything else into it if it's fully charged?
No.
No, you can't. Okay, so if I were to do that, at first it would look like, oh, okay, well, I've got this short circuit here. Well, but then what happens is that, oh, it's not taking anything else. I can't put anything else into it. What does it mean if I have something that I can't put any current into? What is that called?
Open.
That's an open circuit. That's right. So when a capacitor is connected to DC, it looks like a short and then suddenly looks like an open circuit. So if you just leave it hooked up, a capacitor becomes an open circuit. So what that really means is that in the long term, a capacitor looks like a short circuit for AC and an open circuit for DC. A capacitor is marked by the letter C. It has the unit of capacitance, which is its ability to store energy in an electric field. And the unit of capacitance is called the farad, named after Michael Faraday. Now, because it stores energy in an electric field, there's probably something that stores energy in a magnetic field. And this would be known as an inductor. Okay, so everybody hold up your right hand, stick out your thumb like this. Got to wiggle the thumb. Now take your fingers and roll them forward. Has to be the right hand. Okay, so if a current flows in the direction of your thumb, it generates a magnetic field in this direction, in a loop around the wire. An inductor, because that is true, if you have a current flowing in a piece of wire like this, I'll draw it the other way, then the magnetic field will go like this. It'll go into and out of the page in loops around the wire. So if that is the case, and I stick another wire right here, and there's a magnetic field that's being generated by the first wire, what do you think will happen to the second wire?
It mimics it.
Yeah, actually, what will happen is that if a current generates a magnetic field, the magnetic field that the second wire is in will actually generate a current. You'll actually have a current that is induced in the second wire. This is why two wires that are placed closely together, if they're not shielded from each other, can do things like crosstalk, because of the magnetic coupling between the two. Okay, so sometimes this is a bad thing. Sometimes this is a good thing. So if we have this thing called an inductor, which is marked by the letter L, this has a thing called inductance, and it's marked by the letter H, which is Henry's. That's the units. Named after Henry. This actually stores energy in a magnetic field. So a capacitor stores energy in an electric field. An inductor stores energy in a magnetic field. Now, if you disconnect a capacitor from a power supply, it will stay charged up to wherever it was. But what happens if I have this magnetic field that's now like zipping around in space around this inductor? It has a north and a south pole. If anyone's ever taken a nail and built an electromagnet out of it, that's essentially what this is. So let's say that we have this north and south pole that have formed, and we have a plus and a minus like this, and now we suddenly disconnect it. What do we know about energy? Can neither be what?
Cannot be destroyed.
Created or destroyed. That's right. It only changes form. Well, now we have no battery, and all of a sudden this magnetic field is sitting there in space, and it hasn't permanently magnetized anything, and it's like, okay, I've got all this energy stored up. What am I going to do with it? What ends up happening is that this magnetic field tends to create a high voltage right here across the coil, and it says, okay, I have to get rid of this energy somehow. And what it does is it generates a really big voltage right here and causes a spark to jump across it to dissipate the energy. Magnetic fields don't like to be disturbed, right? Once they exist, they like to stay there. They don't like to be changed. So what that means is if I were to hook up a DC battery to it to make an electromagnet, this thing is perfectly happy doing it. But if I try to take it away or change it, it says, no, I don't really like that. I'm going to fight it. So remember where a capacitor looked like an open circuit for DC and a short circuit for AC, if I were to take this and hook this up through the magic wall and say, okay, here's my power supply, here's my DC power supply, that inductor looks like a short circuit. If I were to instead do this and hook it up to an AC power supply, that inductor in the extreme looks like an open circuit. So the ability of something to fight the flow of alternating current is known as impedance. Okay, so resistance is for DC. Impedance is for AC. And just to be confusing, they're both measured in ohms. Now, it is also true that for a resistor, resistors don't care if it's AC or DC. So in that particular case, impedance equals resistance in a resistor. But in a capacitor or an inductor, they do not. So what is interesting about these two devices is that they are very useful because an inductor and a capacitor have impedances or reactances, that's another form, we'll use reactance. We'll use the letter X instead of Z. So XL and XC. Okay? You don't have to remember this. 2 pi FL. And this is 1 over 2 pi FC. Okay. So these are basically the impedances of these things. What weird letter do you now notice is in both of those?
Pi.
Pi?
2 pi.
Nah, pi is just a number. What's that letter
Frequency.
right there?
The
Frequency.
weird,
Frequency.
Frequency. Uh-oh. Which basically means that these reactances, these impedances of an inductor and a capacitor are frequency dependent, which actually has some very, very profound results. The first of which is, it turns out that a capacitor has a negative impedance and an inductor has a positive impedance. And if I were to draw them like this and put them in series, I'd have a positive here and a negative impedance here. And by changing the frequencies, notice that F appears in both of them, I could pick them so that they completely cancel each other out. And that's really important because what happens if I have no resistance to flow of current? What does that mean?
All the power gets through.
All the power gets through. That's right. Everything gets through. But only at one frequency where they match. So now what I end up with is a circuit that has a frequency response that looks like this. It's bad, 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 bad. Oh, look at that. It's really good right there at that particular frequency. Huh.
Is that resonant?
That's called resonance. That's exactly right. Like if I do this. That's a resonant frequency based on the mechanics of that cup that I just hit. This is a resonance that is defined by the values of those two things. Because this is 2 pi FL, and this is negative 1 over 2 pi FC. So by picking my inductor and my capacitor at a particular frequency, I get a circuit that now does that. That is peaked. That it works really well at one particular frequency. This is used for something called an oscillator. This is also used for something called a filter. We use these every single day. This is in your microwave oven. There are dozens of them in your cell phone. There are dozens of them in your computer. And to answer that other question, so now let us take our current. See, I told you I would get to it. Let's take our current flowing through a wire. All right, what does a current flowing through a wire make, everybody? Any current makes what kind of field?
Magnetic.
Use that hand? A magnetic field. So we're going to make our current flow this way. And where our magnetic field is going to go like this. Okay, so now what we're going to do is we're going to introduce something that when you place it in line with it, tends to absorb magnetic fields. And okay, so where's Dan? Was it Dan?
Yep, it was Dan.
Dan, were you asking the question about your power supply?
Yeah.
There you go, man.
Nice.
You know what that is?
A choke?
That is called a Ferrite Choke. What it does is it's a tuned device that's made of usually like a powdered iron and cobalt that's baked into a shape. And if there is a magnetic field at a particular frequency that is flying around the cable because of the current that's flowing through the cable, what happens is that that magnetic field gets concentrated in that material and gets burned up as heat.
Oh. Nice. Good to know.
Yep. So there's a very good use for a tuned circuit. Okay.
Well, why don't we have those on cords anymore?
We do. They're everywhere.
Mm.
But in a lot of cases, you don't need them. But most switching power supplies do have them. In fact, virtually every switching supply cord will have it, because switching supplies operate at very high frequencies, like 30 or 40 or 50 kilohertz. And so, in order to keep from radiating a lot of energy, most switching power supplies, which are most DC power supplies now, will actually have a ferrite choke. Okay, let's see.
Now, does
Batteries.
it have to actually be on the cord, or can it be within the power supply itself?
You can put it. I mean, you can put it there, but typically, what you're looking to do is you want it as close to the power supply as possible. You typically won't put it inside, because honestly, it's easier to just clamp it around something. But yeah, I mean, there's a lot of filtering that goes on in the power supply as well before it even gets to that point. This is just, if anything gets out of it, it's as an extra added thing. So like, for instance, on my computer, in order to choke induced radio frequency energy out of my computer, I have my radio is connected to my computer by a USB cable. I have 5 RF chokes, clip-on chokes, that are wrapped around my cable. Why do I have 5?
My grandpa wants to know when y'all actually start.
Start what?
The Zoom meeting.
9 o'clock?
Tomorrow, you mean?
9 o'clock?
9 o'clock?
9 o'clock.
Yep. You got multiple frequencies on those cables?
What?
It's because you have multiple
9.
frequencies on that cable? Sorry.
Nope, that's not why.
9.
Why do I have 5 chokes on that? Why do I have 5 chokes on my cable? Because 4 wasn't enough. Because what happened was, when I was transmitting, I would lock up my computer. And I kept adding them until the problem went away. So 4 wasn't enough, so I made it 5, and that was enough. All right, batteries. Let's see, what is the typical car battery voltage? Everybody, how many volts?
12 volts.
12
12
volts.
volts. Are car batteries rechargeable or not?
Yes.
They are rechargeable. Okay, so lead acid is the chemistry in a car battery. It's a reversible chemistry. Lithium ion, nickel metal hydride, NiCad, those are all rechargeable batteries. A carbon zinc battery, or like a silver air battery, like a hearing aid battery, those are one time only. Like a lithium metal battery, which is like a button cell that you would you put in like a watch that would last for 20 years. That's not rechargeable. That's a one-time thing. Still recyclable, but not rechargeable. And okay, finally, electrical components used to connect or disconnect electrical circuits. All right, the first one, that's called a switch, and something that is designed to protect circuit components from current overloads, that's known as a fuse. So tomorrow we're going to get into semiconductors and schematics. And from then, we're going to start to get into how we start building equipment and filters and cool stuff like that.
What page was that where you did the electrical component?
I believe that was 17. Let me make sure.
Yes.
17?
Okay, thanks.
Yep, so tomorrow we're going to do electrical components like semiconductors and then schematics. Any other questions before before we wrap for the day? There's got to be some questions. Not a
Fuse or
single
circuit
question.
breaker preferred?
A circuit breaker is preferred because, or when or why?
It can be reset.
You can reset it. You don't have to replace it. That's very true.
But which are more accurate?
You know, it's the thing about a circuit breaker is if it trips a few times, it's no longer accurate. A fuse is always going to be accurate. But if you happen to be, let's say, oh, I don't know, working on the railroad or something, and you have a circuit breaker trip, and you're 50 miles from anywhere, you hit a button and you can reset it, and you know why it was tripped, you know, and everything's okay, then you can just reset it and keep going. Whereas if you blow a 30 amp fuse and you don't have another 30 amp fuse, what are you going to do? So, so it is also true that that fuses can typically be made to operate a lot faster than breakers can. So that being said, like when I build electrical equipment, I use mostly fuses because I can pick how fast they trip. Certain ones I really need to trip very fast. Excuse me. Any other questions? All right, I'm going to stop recording.